So we're going to talk about root functions, and this is generically, this section I think only deals with the square roots, but you're going to have to deal with all of them anyway, so let's go over the whole shebang. So the root functions, I think of them, I'm sure people think of them as separate, but I think of them as inverses of the polynomial functions, and that's why I quick did the polynomial function video before this. If I want to find the inverse function of this polynomial function, which is y equals x squared, I'm going to switch the x and y, and I'm going to take solve for y, which means I have to take the square root of both sides. And so I get y equals the square root of x, but that's plus or minus. Okay? And so I end up getting something that looks like this. All right? Except if you can tell, of course you can, as you note that this vertical line crosses the graph twice, so it really is not a function. And so for us to have a function with a square root, oops, didn't want to do that, with the square root, then we have to restrict the domain and range, and we don't need to restrict the range, we can just restrict the domain and get rid of this bottom half. The range will result, but I really do need to restrict the domain. And we restrict the domain by removing that negative, all the negative values, so we just have the positive values, and my function looks like y equals the square root of x. And this goes for all exponents or roots that are even. So y equals the fourth root of x ends up looking like this. It's the same except it's skinnier. And y equals the sixth root of x, again, looks the same except it's skinnier, or flatter if you wish. It doesn't shoot up the y-axis as quickly. So all the even roots have this implied domain, this restriction on the domain. And how do we determine the restriction on the domain? Well, we need to think about the parent function, which is this one here, this y equals x square root of x. Y equals the square root of x has this domain restriction such that it can't be any less than 0 and has to be greater than 0. Why is that the case? It goes from 0 to infinity, including 0. So why is that the case? Well, if I put negative 7 in for x, let's say x equals negative 7, then I get y equals the square root of negative 7, which is perfectly fine. There's nothing wrong with that number. We're going to use that all the time and get to negative numbers and complex numbers and blah, 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 blah. At least I will use it all the time. You may not, depending on how far you're going to go, but you're going to at least have to deal with it when we take use the quadratic formula. So this y equals the square root of negative 7 is a perfectly fine number, but it's imaginary, which means it's not real. That doesn't mean it doesn't exist. It means it's not a real number, a category of numbers called real numbers. And if it's not a real number, our Cartesian coordinate plane only plots real numbers, a real x and a real y. So if this is a non-real number, I get this point x comma y that's equal to, what did I put in there, negative 7 comma square root of negative 7. Well, I can't plot this point because that number is not real. I can't plot it on my xy plane. There is a plane called the imaginary plane. You can certainly plot it there, but we're not concerned with that with this course. So I need to have all my numbers real, which means I can't put any negative numbers in, which creates this situation where the domain has to be greater than or equal to 0. All right. Now, how do I deal with other functions such as these, y equals the square root of x minus 5? Well, my domain must be, my square root thing must be greater than or equal to 0, and that quote thing is called an argument. The thing that I'm doing stuff to. So for instance, y equals x to the 7th, x is the argument. Y equals x plus 2 to the 5th, x plus 2 is my argument. So in this case, I'm taking the square root of that expression, x minus 5. X minus 5 is my argument. Okay? That's the name of that little piece of the expression. So for these functions, my argument must be greater than or equal to 0. That's what we found out when we just looked at y equals the square root of x. This part here, this x, this stuff under the square root, in order for it to be real, for this number to be real, this has to be greater than or equal to 0. Okay? So we can look at it the same way and analyze this. This argument, x minus 5, must be greater than or equal to 0, which means my x value must be greater than or equal to 5, because I would add 5 to both sides. If I had a more complex root function, like y equals the square root of 3x minus 15, again, 3x minus 15 must be a real number, so it must be greater than 0. My argument must be greater than 0, or equal to 0. And so I can solve by adding 15 to both sides, and then dividing both sides by 3, and I get x is greater than or equal to 5. Just happened to be the same, just coincidental, because I pulled those numbers out of my butt. So now let's look at, so those are even root functions. So 2, 4, 6, 8, 10, 12. What about odd root functions? Again, not necessarily part of this section, but might as well cover it here. So if I start out with that function, a polynomial function that's cubed, has an exponent of 3, I switch the x and y, so I get y equals, I get x equals y cubed. Then I take the cube root of both sides, I get y equals x cubed. I'm sorry, I keep doing that. You don't know that I keep doing that, but y equals x cubed. Now, because this cube root and this cube carry the negative forward, we don't actually need to restrict the domain, because it doesn't generate any imaginary numbers. And we could also see that by looking at the graph. Y equals x, the cube root of x looks something like this. Okay, it might not be going through the right values, but it looks something like that. And y equals the fifth root of x looks very similar, except skinnier, or flatter if you prefer. So these are all inverse functions of polynomial functions. The odd ones do not have domain restrictions inherently to the function, and the even ones do. So you need to keep that in mind, and that would explain to you why the questions that we ask you are the way they are. All right? Hope that helps. Take care. Bye.